My name is Kate. I'm going to be doing a chemistry lesson with you today. And since this is the first lesson, I'm going to start by introducing the subject to you. You should know that I'm not alone here.
Oh.
My boyfriend Christopher is in the background, just in case you hear a little throat clear or a giggle or two. I told him to laugh at all my jokes, so that, so at least I think I'm funny, even though I really actually know I'm not. Anyway, okay, so we're going to start with what is chemistry, like just really get down to sort of what it's all about, and really start to try to build on it in what hopefully seems like a logical fashion. Usually when I have a live class, I ask them what to name things that they think are chemicals. So I guess I'll say here, think about things that you think are chemicals. You're probably coming up with like really exotic things like ammonia or other kind of cleaning materials, or I don't know. Christopher, what do you think of when you think of chemicals? Can you come up with anything?
Things that are toxic.
Yeah, toxic, like bad for you, so on and so forth. That's a popular misconception. It actually turns out that, as humans, we tend to call those things chemicals, but really, chemistry is everything. So, for instance, the chalkboard, this is actually a whiteboard that I'm writing on. I'm made of chemicals. Maybe the chair you're sitting in right now, or if you can look out a window, the tree you see outside, the air that you breathe, so many things are actually chemicals. So for the intents and purposes of this class, we're going to encompass all of those things when we talk about chemicals. Okay, now, there was a lot of debate, through the years. Like, chemistry was very interesting to the early Greek philosophers. And they used to sit and ponder about what is matter. They'd sit and they'd look and they'd kind of look at each other and they'd look at things and they'd try to figure out philosophically what is matter. And they would say, well, we think that some of the philosophers, early philosophers, said, well, matter is, is something that you can touch or feel or interact with, and if you tried to look at it closely, you would find that matter was continuous. So something that's solid, even if you could look at it with a really tiny microscope, is still perfectly solid. And there were other philosophers who said that matter was actually made up of dozens and millions and trillions of small particles that were all so closely packed together that to the human eye they look like they're solid, and they're packed tightly enough that you can't break through them. So so they thought that sort of made more sense in terms of what matter could be broken down into. I want to take a break here because I've been using the word matter a lot here, and I want to make sure that everybody understands what matter is. Matter tends to be a word that we use to describe pretty much anything, and that way we're not getting locked into any particular thing. So matter can be a solid, it can be a liquid, or it can be a gas. So anything you can think of that's a solid, a liquid, or gas, that's matter. So, okay, back to the early philosophers. So they kind of sat around, they looked at each other, they scratched their head, they said, well, it makes more sense, well, this makes more sense, and so on and so on and so on. Well, it was John Dalton, actually, in 1803. John Dalton was the first person to actually do a chemical experiment to determine whether matter was made up of what's continuous or not. So, just to kind of give you a little bit of an idea, those people who are arguing that matter was actually made up of small particles, what they were proposing is that, so to the human eye it looked like it was solid, but if you really got into it, it was actually different particles. And a good analogy to help you understand that is if you have ever looked really closely at a newspaper picture. So if you look at a newspaper picture, like, you hold it out, you can see the picture. But if you get really up close, put that picture up and then try to focus your eye because it's awfully close, you will find that the newspaper picture is actually made up of a bunch of tiny dots. Okay? So that was sort of the similar proposal. Only there was no way that you could look closely enough into matter to see the actual particles. Okay, so anyway, so here we are. We've got Greek philosophers arguing for, against, so on and so forth. John Dalton actually does some experiments, and John Dalton actually finds, in fact, that matter is, that those folks who said that matter was made up of discrete particles were right. And so this became our first conclusive proof of the existence of these small particles. These small particles were given the name by the Greeks, by the way, atomos, A-T-O-M-O-S, which means cannot be divided, apparently in Greek. And so John Dalton went with that, and he called these smallest particles atoms. And so what came out of that was John Dalton's atomic theory. So I write on the board, and whenever I write on the board, that means it's something that I think that you people should take the time to get interactive on and actually write down in your notes. So I try to use writing on the board as a way of transferring the information so that you get to see it. But I also encourage you as students to actually write things down that I write down, and that way your brain is thinking about it, but also your hand is writing it, and it's another form of learning. It can be useful. So. Okay, so there are four main elements to John Dalton's atomic theory. First of all, each element. Now, an element is just another word for a collection of atoms. Each element is composed of extremely small particles called atoms. So for instance, a good example of an element is copper. Copper is an element because if you take a copper wire and could break it down, you'd find that it was made up entirely of small particles of copper atoms. The second item, all atoms of a given element are identical. So, well, why is this important? You know, all atoms of a given element are identical. Well, it actually kind of helps. I mean, you want to know that if you have a chlorine atom, if you have one chlorine atom here and you have another chlorine atom over there, that you can reasonably expect that the chemistry of each are going to be the same. So that was just sort of important for John Dalton to include that as part of his theory. So, atoms of an element are not changed into different types of atoms by chemical reactions. So what that means is that, I guess the early alchemists kind of thought that they could change atoms into different kinds of atoms. So for instance, there was a big push because gold, of course, is valuable, and lead, of course, was available, and there was a big push for the early chemists to try to change lead into gold. And I think most people know that that can't be done. But you know, back in 1806, it was important for Dalton to make this part of his theory, something that he found. So atoms of an element are not changed into different types of atoms by chemical reactions. So when we have a chemical reaction, we don't have an atom change. What we have are combinations of atoms which break up and reform a new combination of atoms. And so we're definitely going to get into a whole lot of that. Item 4 of Dalton's atomic theory. Compounds are formed when one or more atoms combine. Type of atom, I should say. So we have the atoms now coming together, and they'll come together in very certain proportions in order to make compounds, molecules, things like that. And so compounds will form when one or more type of atom combine. So water is a great example. Most people know that water is made up of hydrogens and oxygens. And so what we have are hydrogen atoms and we have oxygen atoms, and they combine to form your compound water. And again, most people know it's H2O, and so the water molecule consists of one oxygen and two hydrogens, which are bonded together. So we're going to get into a lot of detail about that, and I hope you look forward to it. So take a little time to copy down all of the elements of John Dalton's atomic theory. It's really pretty cool that he was able to really come to all of this, because it really brought chemistry out of the philosophical phase and into the actual experimental phase. And that's really where things get exciting. So anyway, thanks for your attention.